Okay, guys, welcome aboard. We are week 9, getting very, very close to getting back into the classroom, which will be very exciting. Let me let Suleiman in here, which will be very exciting. I think we will be all done with our notes by then, which would be really nice. So we're actually getting pretty close to finishing the basic electricity notes, which will be really cool. Then the only other notes that we really have is something called lockout tagout. And then basically we're into all of our laboratory work. So that will be extraordinarily cool because, well, I didn't like this distance learning. One thing is it allowed us to get all of this stuff done during distance learning. And then when we get back, we'll be straight into all the labs. So you'll just be working from lab project to lab project, which personally I think is the most fun part of the class. You know, the theory's fun, but the theory is just there so that we can actually do stuff with electricity. And once you get those basics, then you can really start experimenting, and that's where the fun really begins. So, well, I didn't like this distance learning, not one bit. I will say that is interesting because when you guys come back, you'll be able to launch right into all the labs. So we'll probably start with the basic electricity lab first, which is a really, really fun one. That's the one where you learn about household or residential electrical wiring, and you'll be able to wire up basically a house. You know, you won't know every little nook and cranny of the electrical code, but you'll know a good amount of it to where you can do a lot of the work. Electricians are one of the actually they are the highest paid trade. And so a lot of money in electrical work and tons of jobs right now for it. In fact, almost any trade right now, it's hard to even find someone to work for you. That's how much in demand they are. So it's a very good time to be one of us. Okay, are we going to do 3-phase electricity? That is a really good question, but no, we will not be doing 3-phase electricity. So usually what you see in our households is well, they call it single phase, but you're going to have one sine wave of electricity coming into the house. And with 3-phase, you have 3 legs of electricity doing those sine waves. And so some of our electricity in the house is single, and then we'll have some electricity in our house that has 2 hot legs to it. So for instance, your dryer has 2 hot legs, your oven has 2 hot legs, and so those will be coming through with 2 sine waves, but 3-phase has 3, and they usually only see that in commercial buildings, which is like the school. Our school has 3-phase power. So some of our stuff here is 3-phase and some of it is not. It just kind of depends on which tool or device you're working at. Usually if it has a really big electrical demand, there's a good chance it could be 3-phase at the schools. 3-phase gives you a couple of advantages, the biggest of which is the motors are way cheaper to run and way cheaper to just initially buy because they're simpler motors, and the electricity is real smooth, so they tend to last for a long time. So 3-phase is awesome, but it's not very common with residential wiring. I was like anesthesiologist. That's funny. So Suleiman, an anesthesiologist is a doctor, so that would not be a tradesman. So trades are going to be like electrician, plumber, carpenter, sheetrock, roofer, even some of the like sewer lines and that kind of stuff with utilities. So that's going to be more of those. An anesthesiologist is going to be like one of the highest paid jobs in the country because not only do you have to have a college education, but then you need to have a doctor's degree. And then on top of that, you need specialty training to be an anesthesiologist, not just a doctor. So when you talk about anesthesiologist, that's in a whole different category, because as a tradesperson, you could basically start working right out of high school or out of community college. So that would only be 2 years of college at the most that you have to have, although you could go all the way up to a doctorate, but you only have to have 2 years. But an anesthesiologist is bare minimum going to have, 4 years of college, 8 years of med school, and then whatever else anesthesiologists go on top of that. It's one of the most technical doctor level learnings. So that's one of the most book educated people that we have in our society. So he's way, way up there. And I'm just going to throw out a guess that an anesthesiologist is somewhere in the $400,000 a year range. So that's going to be quite a bit of money. But remember, you do have to spend like crazy to get all of that education to get there. So whole different level. Okay. For engineers, you're very good with the petrol engineer. When you talk engineers, the highest paid engineer right out of college is a petroleum engineer, which is a specialty chemical engineer. And then the second most is a chemical engineer. So when you talk engineers, the highest is petrol or petroleum engineering, and the second is chemical engineering. So good job, guys. But if you look, I do a presentation one time in this year, and of the top 30 top paid college degrees, all the stuff that we do, engineering, all the different types like electrical engineering, mechanical engineering, electrical circuit board engineering, programming engineering. Like if you look at the top 30 jobs, we occupy probably 85% of them. You know, I think the only one on the art side is economists breaks the list, but otherwise it's going to be all kind of STEM related fields. So I'm just telling you guys right now, the skills that you have are in very, very high demand, and it's never been a better time in history to be our type of people. There's lots and lots of jobs out there. Let's see here, fossil fuel job. If you mean petroleum engineer, that is definitely a fossil fuel job. A chemical engineer is not necessarily. A chemical engineer could do all kinds of things. They could work on like cleaning up oil spills. They could work on new products for cleaning. They could work on like a new types of plastic coating or a paint coating that keeps the space shuttle from burning up in the as it enters the atmosphere. Could be anything. Chemical engineers, I always think of them like the magicians of the world. They come up with all that crazy stuff, make surfaces super slick, super resistant to heat, super, like pans that you can cook something on and nothing sticks to. I mean, they do everything. Chemical engineers, they do kind of like all those magical things. Come up with the correct sheathing for the wires that we use to keep the, they'll come up with the correct insulators for keeping the electricity in the wires. Okay, let's see here. Oil, yes, petroleum is fossil fuel for sure. So somebody asked, is it going to be here forever? That's something I always want you guys to think about, because that's really important. You guys will, most people live about 100 years, give or take. I think the average is actually 87 or 88. And who knows, you guys may live way longer depending on the medical technologies, but you got to figure that you want to get into a career that's going to last that amount of time. So somebody brought up petroleum engineer may not be around forever, and that's definitely true. It may not be. However, I have a feeling it will be around for your entire lifetime. That's my guess. Now, how popular it will be less and less popular, probably, less and less demand, but I'm pretty sure that will be around for your guys' entire lifespans, because it's not going to be just turning oil into gas. It's going to be using it in a lot of different ways, and there's a huge infrastructure in place, which makes it a lot cheaper. So it'll be around for a long time, but after your lifetime, I'm not sure. That it may not be, but I would think for your lives, you'll be okay. Okay, let's see here. Somebody brought up Americans die early. Yeah, that is one sad thing, guys. Technically, our lifespans have been increasing until very recently. Americans' lifespans have actually dropped. So it was steadily going up, and I think it got up to about 88 or 89. Don't quote me on this. And then it did drop a year or two over the last couple years, 8-10 years, something like that. And the reason is not because of technology. The reason is because we're fat. Americans get too fat, and fat fat causes all kinds of problems to your health, especially as you get older. So you guys are young, you got good metabolisms, but as you get older, like me, your metabolism slows down. Like me, I was always very fit, and now I put on too much fat, so I got to lose that fat because it starts to have a health effect on you. And just like you guys were saying, Americans can die early. That's why. It's usually because of fat. Americans are fatter in general than the rest of the world, and that causes big health problems. In fact, I just heard a recent, we always look for the newest jobs. So I heard one of the newest jobs is a doctor that specializes in treating fat people. That's their specialty. So it's definitely a big problem in this country, and it's not going away anytime soon. So just things to keep in mind. Cool. Riley just posted the actual numbers of it. So looks like 76 for males and 81 for females. Okay, yeah, exactly. All kinds of jokes for that. Let's see here. Okay, so let me go grab this electrical stuff because I want to get through with it so we could be done. Where the heck did my notes go? Is that it? No, that's not it. There it is. Okay. So let me share my screen here. That's a good comment. Life is definitely short and it whizzes by really, really quick. So make sure you guys, that's one thing I try to stress with you guys. We are in control of our own destiny as shop students. A lot of other people out there, they don't realize how powerful that they are, how powerful the human willpower is. We can do anything we want. Every one of you guys has that power, especially since we live in America. And we are given a very short amount of time, okay? We just looked at the stat. What was it, like 76 or 81 years? So very short amount of time. It sounds like a lot, but that goes by quick. You guys have already spent, what, 12 of those. So it goes by quick. And you have a very finite amount of time, and you want to use that to your greatest ability. Whatever you feel you are destined to do, you want to do it. You want to accomplish that. It's very important for every person. Every person has something that's important to them. Like for me, I like to care for animals. That's one of my passions. And I want to make sure my life, some of it was spent doing that and accomplishing that. Every one of you has something like that. I like building things. I like making things. That's stuff I like. I want to spend time doing that. You have a very short amount of time, and you want to make sure you accomplish all those goals that you have in your heart, because every one of us will have those. And us as shop students should know, we know how to solve problems. And that's one of the biggest problems in life, is using your life the way you want to use it, because it's a very short amount of time. Okay, so I will stop speaking there and we will move on. So I do believe we checked out series circuit. The thing I want you to remember with a series circuit is that there's only one path. So if I cut that line anywhere in the circuit, everything else dies. Okay, that's the important part of that. Now, let me see, I see chat going. Let me see if I'm missing something. Okay, hey, that's good. That's good thought there, Reed. I like that. It's good reading into the problem. Good insight. Never thought about it that way. Okay, guys, so series circuit, remember, if I cut it anywhere, so if that light bulb goes out, is there going to be any electricity flowing in this circuit? The answer is no. If I throw the switch and raise it to the up position, is there any electricity flowing through that circuit? No, the answer is no. If the fuse blows out, is there any electricity flowing through the circuit? No, no electricity is flowing through that circuit. Okay, so one cut kills everything in that circuit. Okay, now let's look at the schematics real quick. Remember, what's this symbol down here? Hopefully you remember ground. Repeat that out loud to yourself so that you remember it, okay? It's very important to remember the names of all these. So this is a ground here, and this one over here is also a ground. Are those two connected?
Yes.
Yes is the correct answer. What if I put a third ground here? Would all three of them be connected? Yes. Okay, anywhere you see a ground, every single ground is connected. Okay, and that's what the ground means. Okay, so now we're getting into parallel circuits. Now, you guys don't remember this because you grew up in an age where you didn't have this kind of pain. But all of us old farts, when we were kids and it came Christmas time, all of a sudden the lights would stop working. All those Christmas tree lights. I don't know how many hundreds you have on your tree, but all of a sudden you'd pull them out from the winter storage and you'd go to look at them, you'd plug them in, and the lights would be dead. All the lights would be dead. And so our parents would give every kid the job of figure out which light is burned out, because on old Christmas tree lights, they were all wired in series. And so if one light bulb burned out, what happened to the rest of the lights? They all burned out. So stupid little kids got stuck with the task all across America of pulling out every single light and trying it with a good light to make sure which light bulb was burned out, because you couldn't tell. So nowadays, all of our Christmas tree lights are wired in at least mostly parallel. Not every single light is, but they're kind of like sections. So every 5 to 10 lights is one section. They're wired in parallel. And the advantage of parallel is that since there's more than one path for the electricity to take, then you can have an outage somewhere in the system and it does not kill the other side of it. So let's look at this very, very simple one here. Okay, we have our 12-volt battery. Notice there's no battery symbol there. It just says 12 volts. So you see what I'm saying about there's no set symbols on all this stuff. It's kind of a hodgepodge. So you got to get good at reading these. Okay, so 12 volts, we know that's a battery, right? And what's this symbol over here?
Ground.
Hopefully you remember that's a ground. Even though it's pointed to the side, it's still a ground. Okay. Now, electricity should go from the positive here, and it should flow all the way to the ground, correct? Should flow out of the positive and flow all the way to the negative, which is the ground. That's what it's going to want to do. We use conventional theory when we do this. That's what it's doing. Again, remember, in actuality, it's doing the opposite, but it doesn't matter for us. Okay, so now let's see, if you look at this squiggle line that says R1, what is this squiggle line a symbol for?
Resistor.
Resistor, and that's why it's called R, so resistor. And then what's this one over here? It's also a resistor. It's called resistor 2. Now, a resistor just means it's a load. So let's just pretend this resistor here is your hair dryer. Okay, resistor 1 is a hair dryer. Resistor 2 is your stove. Okay, the little burner on your stove. So a resistor usually is going to transfer electricity into heat, and then you'll use it for something. So R1 is going to be our hair dryer. R2 is going to be our stove. Okay. And so we've got electricity coming out of our power supply. It's going to flow through both of those things and then end up into the ground. But let's pretend that our resistor 1 here, our hair dryer, let's say your sister's in the bathroom drying her hair, and she overheats the hair dryer and she blows the fuse in the hair dryer. Okay, so by blowing that fuse, it's going to open this line, and no electricity is going to flow to the ground on this side, right? Because it's going to get stuck wherever that open is. But what about the other side? Can electricity still flow this way?
Yes.
The answer is yes. Okay, so okay, I'm turning chat off because I want you guys to pay attention to this. This is really important here, and it's how you're going to diagnose electrical circuits. Most circuits in the real world are very complex, complicated circuits, especially if you're working on like cars or computers or something. So you have to understand this stuff. Okay, so let's just pretend I put a big slash right through this R1 here. Okay, so that one's open. But let's check R2. To know if R2 is still working, we have to trace its paths back. We have to trace its negative path back and its positive path. So let's follow R2. Does it have a path back to negative? And yes, it still would, right? It still would, because it does not have to go through R1. It does not have to go that way. The electricity can simply go this way. So does it have a path from here to negative? Yes, it does. Does it have a path from here to positive? And yes, it does. So because it has a path to positive and a path to negative, we know R2 will still work. So this is the magic of a parallel circuit, is it's going to allow things to flow, or it's going to allow electricity to flow multiple directions. And sometimes we want that, sometimes we don't. Sometimes it's important to have things in series. For instance, if I had a fuse that was over here, right? If I put that fuse over here on the R1 side, it would not protect R2. So R2 could catch fire and burn the house down. So sometimes you want series circuits, sometimes you don't. So there's not one that's better than the other, but they each have different characteristics, okay? So here's some interesting facts on the parallel circuit. So first off, there's more than one path. That's what makes a parallel circuit, okay? There's more than one path. And then each load device receives full source voltage. So on this one here with 12 volts, R1's going to get 12 volts, R2 is both going to get 12 volts, okay? And then each load device may have its own path to ground. So you could technically have this one have its own path to ground and this one have its own path to ground too. That's okay. That may or may not be the case. It just depends, okay? Now let's go up here. In a series circuit, you will not get the same voltage at everything, okay? So each one of these things takes a little bit of voltage. So the light bulb's gonna take most of the voltage. A switch is gonna take a tiny, tiny little minuscule fraction of a voltage, and a fuse is gonna take a tiny, tiny minuscule fraction of a voltage. Anytime you hook one of these things in, there'll be a slight bit of resistance, so there'll be a tiny bit, okay? So this will lower the voltage just a little, this will lower the voltage a little, and then this will take the rest of the voltage. So it will not necessarily get full voltage. But in a parallel circuit, they all get the same full voltage, okay? And what's gonna change is the way the amperages are shared between those, okay? Okay, so let's take a look at this little circuit here, and I'm gonna have you do a little diagnostic work. This is where people make the majority of money in electricity. If you are good at this stuff, you will make a lot of money. If you're not good, you won't make as much money, and you won't be hired as much, because this is complicated, but the people that can do it can solve electrical problems really, really fast. So we've got 3 resistors here, right? We got a 12-volt battery, we got a resistor, and a resistor. And then we've got 2 grounds. So let's just say that I put a cut. Can we call it, we'll just call this one resistor 1, resistor 2, and resistor 3. Okay, I'm gonna turn chat back on because I want everyone to be able to whisper me. Okay, so you guys whisper me answers when you've got these, okay? So again, resistor 1, resistor 2 is on the top, and resistor 3 is on the bottom, just so we know, okay? Now, I'm gonna put a cut in this resistor right here, where my mouse is. Okay, so resistor 2 just got cut. Somebody, so a rat chewed a hole through it, okay? Which resistors will continue to work? I just cut a hole through resistor 2. Which ones or one continues to work? Getting some good correct answers. All right, so if you said resistor 1 and 3, you would be correct, okay? And the way we know that those work is we have to look for a path back to positive and negative. So does this resistor here have a path back to positive? Yes, it does. Does it have a path back to negative? Yes, it does. So this resistor will work. What about this resistor? Now we're on resistor 3. Does it have a path to negative? Yes. Does it have a path to positive? Yes. How about this one? Since this one's cut, it's not going to have a path back to negative or positive, okay? All right, let's do, what if I cut the line right here? Okay, I took a pair of tin snips or scissors and I cut the line right here, okay? Which ones are still going to work? If I cut the line right here, which resistors are still going to work? Good, I'm getting some good answers. If you said 1 and 3, you would still be correct. Okay, all right. Now, let's try this one. If I cut the line right here, which resistors would still work? If I cut the line right here. Good, I'm getting a lot of right answers. Very nice. If you said 1 and 2 would still work, you'd be correct because they both have a path to positive and to negative. Okay, what if I cut the line right here? Which ones would work? Nice, I'm getting some good answers. Correct answer would be none would work because this first one here would not have a path to negative. These second and the third ones would not have a path back to positive. So that's good. You guys are starting to see how that works. So by the way, what kind of circuit is this that we're looking at here?
Series parallel.
It is. It's a series and a parallel circuit. So far we've had a series circuit with only one path. We've had a parallel circuit with multiple paths. And then we've had a series and parallel circuit, which is probably one of the most common because we want our fuse. See, if we replace this resistor with a fuse, now this one fuse would protect both circuits, okay? Oh, actually, I'm sorry guys, I didn't realize we're actually out of time. So I will see you back tomorrow. Good job on that. Nice work, okay? Good, we're just about done with this stuff. Nice, excellent job. I'll see you guys tomorrow.